A few years ago, when my brother and I were much younger, we would have regular arguments. When we were left at home alone and there was no one to control the situation, things could escalate very quickly. At some point in the argument, each of us had to make a decision as to whether we were going to hit each other or take the more mature route and not fight. Every potential outcome is described by this payoff matrix. We assume rationality, perfect information, and simultaneous decision making. If I, brother 1, chose not to fight, while my younger brother chose to fight, I'd be injured with a payoff of minus 50. My younger brother, brother 2, would be relieved of his anger and receive a positive utility of 50. On the other hand, if I, brother 1, decided I wanted to fight, while brother 2 chose not to, I would be relieved of my anger, receiving a positive payoff of 50, and he would be left injured with a payoff of minus 50. We could both choose not to fight, with neither of us withstanding any injuries, but that would also mean we do not get to relieve our anger, and so the payoff would be 0 for brother 1 and for brother 2. What if we both chose to fight? This would result in the worst case scenario, as the fight escalates further, and we would both end up with even worse injuries, resulting in a negative payout of minus 100 for all parties. This payoff matrix is an example of a chicken game, and it has two natural equilibria in pure strategies. The outcome of both of us choosing to fight is not a Nash equilibrium, as either of us could improve our payout by switching to not fight. The outcome of both of us choosing not to fight cannot be a Nash equilibrium, as either of us could improve our payout by choosing to fight. This leaves us with two Nash equilibria, where brother 1 chooses to fight and brother 2 chooses not to fight, or when brother 2 chooses to fight and brother 1 chooses not to fight. At either of these outcomes, no player can improve their payoff by switching their decision.
What we don't learn from a pure strategy, however, is how many times each outcome is played. We can do so by using a mixed strategy. The utility of brother 1 choosing to fight is represented by UF1, while the utility of him choosing not to fight is UN1. Both of these are written as a function of K, which is a mixed strategy of brother 2 to fight. Some percentage of the time, brother 1 will choose not to fight, represented by K. In one outcome, he receives a payoff of 0, and so we multiply this by K. However, in the other outcome, he receives a payoff of minus 50, and the probability of this occurring is 1 minus K, and so we also multiply these. The same process is followed for UF1, the utility function of fighting, and we equalize the two resulting equations. In turn, solving for K, we get 1/2. This means half of the time, brother 1 will choose to fight, and the other half of the time, he will choose not to fight. As they have the same payoffs, the same probabilities apply to brother 2. What we learn from this is that both Nash equilibria will occur an equal amount of times. In conclusion, neither player has a dominant strategy, and so mixing strategies provides the best outcome for all parties.